watching Cram Science.
In our earlier 3 videos, we have already solved 9701 Chemistry question paper 4-2 of the examination series October-November 2022, and next in this video we'll be solving the remaining 2 questions, question 8 and 9. So for question 1 to 7, watch our earlier 3 videos, and let's continue with this video with the remaining 2 questions. So here is question 8, which is based on NMR, and it says when answering this question, it should be assumed that together all the hydrogen atoms in a benzene ring results in a single unsplit peak at the 7.2 ppm in a proton NMR spectrum. The structures of 5 isomeric ketones PQRS and T are given here. So these are all ketones where we can see there are CO groups in each of the isomers, and there is a benzene ring with the formula C6H5 in all the isomers. Now let's start with question A. Here it says identify all the chiral carbon atom on the structures above. Label each chiral carbon atom with the asterisk sign. Now if we have a look at PQRS, you can always see that there is one carbon here with 3 different groups, but then we have 2 CH2 group on these carbon, so it's not a chiral carbon. Again here each carbon have minimum 2 to 3 hydrogen, so not a chiral. Again same in the case of R also. In the case of S, again we have carbon with 2 hydrogen or more. That's not possible, so we are left with T now, and here in T we can see that there is a carbon here which has one H group, one aromatic ring, the third group is CH3, that is methyl group, and the fourth group is ketone group. So the carbon here which I pointed out here with an arrow is a chiral carbon, and we can mark an asterisk sign here. And to do that, I had to rub all the marks on it. Now let me mark with a asterisk on that carbon. Next, go ahead with the B part where it says the proton NMR spectrum of one of the 5 isomers PQRS and T is shown in figure 8.1, and let's have a look at figure 8.1 properly. Let me scroll down here, and the question here says question A1. Identify which of the compounds PQRS and T gives this spectrum. Draw the display formula of the compound you have identified. Identify the protons responsible for peaks at 3.7, 2.5 and 1 on the structure you have drawn. But before identifying the compound, let's first study the NMR given here, NMR spectra, where we know that the peak at 7 point something here, that's a benzene peak, that is peak due to the aromatic ring. Other than the aromatic ring, we have 3 more peaks, that is we have 3 types of hydrogen atoms, 3 types of proton in our compound, where one of the peak at 3.7 here, this 3.7 peak is a singlet peak. We should understand it's a singlet peak. So the proton at 3.7 peak is a proton which is having no proton on the adjacent carbon atoms. So now let's have a look at the structures of PQRS and T. Let me scroll up again. Let's have a look at the structure of PQRS and T. Now looking at the structure of all the 5 isomers, I found that in R we have one of the proton here which is having no proton on the adjacent carbon. That is, the carbon on the benzene ring will have no proton because it's bonded to the CH2 group. Then there is a ketone group besides this carbon, again having no proton. And if you have a look at the other 4 isomers, you will see that there is no such proton which is going to produce a singlet at 3.7 ppm. And also at 3.7 is a proton bonded to a carbon which should have a CO group adjacent to it. So again that implies to the R group, because we have a proton here which is having a CO group adjacent to it, and then a benzene ring besides it. So 3.7 is due to the CH2 proton bonded to CO group and aromatic ring on the other side. Then the peak at 2.5 here, that's a quartet peak, that is a split of 4. Now that shows that this proton should have 3 proton besides it. So again here we have one more hydrogen which is having 3 protons on the adjacent carbon atom. So the proton here gives 3 plus 1, that is quartet peak. And so this peak is because of 2.5 here, and the proton at the end, that is CH3, is going to produce a triplet here because it has a CH2 group here besides it. So 2 plus 1, it will give a triplet splitting here. So the peak at 1.1 is 1 is due to CH3, and the peak at 2.5 is due to CH2. Here again a CH2, and this is C6H5 protons present here. So let's go ahead and answer the B part of this question, the second part of this question. So as we have already identified, the compound here is R. So here it's written, draw the display formula of the compound. The display formula in the sense showing all the carbon and all the hydrogen. So we need to draw a display formula with a benzene ring first. So let me draw a benzene ring first with the display formula here. With the you can draw a ring also, or a double bond like this. And then we have a carbon CH2 group here. Next we have carbon with a double bond O. Then again we have CH2 group, and then CH3 group at the end. This is structure R. Now we need to label these peaks with the 3.7, 2.5 and 1. So here we have 3.7 ppm peak. These protons have the peak at 2.5, and this 3 protons is having the peak at 1. So this is how we are going to label it. Yeah, so this part is done. Now name the splitting pattern of the peak at 3.7. Explain why it has this splitting pattern. So the splitting pattern at 3.7, as we have already seen, this is singlet here. We can see that it's the singlet, so we'll write it as singlet. And this is because there is no hydrogen or no proton on the adjacent carbon atom. So the splitting of this proton will be singlet. So this is the reason. Let's go ahead with the next C sub question. Choose from the letters P, Q, R, S and T to identify the 2 compounds that each have a doublet peak in the proton NMR spectrum. Okay, so again we need to have a look at the structures where we will have a doublet peak from the 2 compounds. Now if we say doublet peak, that shows that there should be a proton which have a single hydrogen atom on the adjacent carbon atom. If we talk about the single hydrogen atom and the adjacent carbon, then here is one proton in P which will have a doublet splitting because there is single proton on the adjacent carbon. Again, if you have a look at the remaining structures, I'll see that again there is one proton here which will have a doublet splitting because on the adjacent carbon there is one proton. So P and T are the 2 compounds where which is going to produce our doublets. So let's write an answer here that the structures are P and T. The next sub question says the compound with only 3 peaks in its proton NMR. Again, have a look at these structures. Now, out of 3 peaks, 1 peak is definitely for the aryl, that is C6H5. Then the remaining protons altogether should produce only the remaining 2 peaks. Now that is only P, I would say, because 1 peak is due to this proton of aryl ring, and then the second peak and the third peak is due to the all of the CH3 groups bonded to this. So then our answer is P here. So let's go ahead and write it in our space here. The compound P is the answer. Suggest a suitable solvent. In the next D part, suggest a suitable solvent that should be used for obtaining the spectrum shown in figure 8.1. If you talk about a solvent, then solvent should be neutral, producing no peaks, or a singlet sharp peak. So there is CdCl3 is one of the common solvent used, or you can say tetrachloromethane group, that are the common solvents used. Here it is CdCl3. Let me rewrite it. CdCl3, that is trichloromethane with 1 deuterium proton, not a simple proton. Okay, let's go ahead with the next E part. It says that the proton NMR spectrum of compound T is compared in the presence of D2O and in the absence of D2O. Describe any difference between the two spectra. Explain your answer. Now, to understand this, we should know that if a compound has either alcohol group OH or any amine group, then the compound, when dissolved in D2O, that is heavy water, is going to replace out this hydrogen with D, and so the peak responsible for this proton will disappear from the spectra. But our structures doesn't have any alcohol or the amine group. It's a ketone and benzene rings compound. So here there won't be any difference with D2O or in absence of D2O. So I'll just write no difference in the spectra, as there are no OH or amine groups to be replaced by D, that is deuterium proton. Okay, let's go ahead with F. We have few structures. We can see in F that there are few structures. Complete the table 8.1 below to give the number of peaks in the carbon-13 NMR spectra of each compound. Now understand, I have seen students getting confused between the proton NMR and carbon NMR. Here we are supposed to look at the carbon only. So types of carbon present in these compounds. So if we look at the first compound, here is a CH3 producing one type of peak. This carbon is going to produce the second type of peak. The third carbon of the aryl group is going to produce the third type of peak. Now this 2 carbon is going to produce the fourth type of peak, because these 2 carbon are in the same environment and is going to produce the same peak. The next 2 carbons are going to produce the fifth type of peak, and the remaining carbon is going to produce the 6th peak in the carbon-13 NMR. So the number of C13 NMR peaks here for this compound should be 6. Now if you look at the next compound down here, what I suggest is, when you have such a complicated structure, look for the line of symmetry. Now if we look at the line of symmetry, I can draw a line of symmetry here. Now look at how many carbon atoms are in a similar environment. So here I would say that both of these carbon are CH3 and in the same environment. So it's going to produce one type of peak. The second peak I can say is going to be produced by these 2 carbons. The third peak will be produced by these 2 carbons I am labeling, and the remaining 2 carbon is going to produce the fourth type of peak. So the numbered which are same carbon which are numbered same are going to produce single peak because they are in the same environment. And so I'll say here this compound is going to produce 4 types of C13 carbon 13 peaks. Now next, if we go ahead, let's again look for the line of symmetry, and I'll draw a line of symmetry here. So the 2 carbon here both are again CH3 and is going to produce the first type of peak. The second type of peak will be produced by these 2 carbons. The third peak I'll label here is third. The remaining 2 is going to produce the fourth type of peak, and the last carbon left over at the end is going to produce the fifth type of peak. So number of peaks, C13 NMR peak for this compound are 5 peaks. Now again have a look at these 2 carbon, the remaining compound here. Again both of these carbon are in the same environment, so the first peak, these 2 are going to produce the second type of peak with a different environment. And now the remaining, I would say, if you have a look at the structure, they are all in the similar environment because adjacent carbons are similar. So here these all the remaining 4 carbon atoms are going to produce the same peak because of the same environment, and so here the number of peaks for carbon will be 3. So this is how you look for the number of C13 NMR peaks for any given compounds. Okay, so here is the end of question 8. Let's go ahead with question 9 here. Now this question seems to be something related to amino acids because here it says tyrosine and lysine are shown in figure 9.1. Now the naturally occurring amino acids found in proteins. You can see the structure of tyrosine and lysine. Now let's go ahead with the question A. The isoelectric point of lysine is 9.7. Now you must know that isoelectric point is a structure of a protein where there should be an equal number of positive and negative atoms on the amino acid. The positive amino acid, the positive part produced by an amino acid is generally due to the amine group which changes, accepts one more proton to form the positive and the carboxylic group generally produces the negative part of this compound. Okay, so isoelectric point here for lysine is 9.47. That is, at the pH 9.47, the amino acid lysine is in the isoelectric point. Okay, draw the structure of lysine at the stated pH in the boxes below. Now pH 7, though going to be a neutral pH, but for lysine, if the isoelectric point is 9.47, it seems to be acidic for lysine. So one of the amine group may accept the proton from the buffer or the solvent. So if we draw a structure for this, then I would just draw NH3 first to show a positive end of these amino acid accepting the proton, and the remaining parts remains as such. So let me draw the remaining part as such. And so we have COOH group also unchanged with just one positive charge on the lysine. Now 9.47 pH is an isoelectric point. So the lysine should have one positive charge and one negative charge. So I'll again draw NH3 with one positive charge, and the remaining I'll draw now for same and NH2 group here, and the carboxylic group now is going to form a negatively charged end. So I'm removing proton from the carboxylic group, and I've added one proton to the amine group, producing one positive and one negative charge on the amino acid, making it a charge neutral for this. Now lysine at pH 12, now that is going to turn out to be little basic, and because of that the amino acid is going to lose proton. if it loses proton, then in that case the amine group remains same, unchanged. So let me draw the amine groups unchanged. And so here is one more NH2 group, but the carboxylic group is going to lose its proton because of the basic pH, and so here I should draw the lysine with one negative charge on the carboxylic part. So after these structures, what we have coming up is when ethanoic acid is treated with PCl5, product D is formed. When D is added to tyrosine, two different isomeric products E and F are formed. Now the E and F are the isomers of each other. E has an ester linkage and F does not have the ester linkage. Draw the structure of D, E and F in the boxes below. So we will have a look at the tyrosine structure again, but if we look at the structure of D, D is produced by reacting ethanoic acid with PCl5, and that's going to produce ethanol chloride. And if you want to draw a structure of ethanol chloride, it's as simple as this. So D is CH3COCl, ethanol chloride. Now let's have a look at the tyrosine structure once again and understand it, where we have one benzene ring bonded to the OH group. So you can say there is a phenol group here, and then we have one NH2 and carboxylic group as usual in the amino acids. So if we have a look at such structures, let's draw the tyrosine part with the D reacting with the tyrosine, producing the isomers E and F. And if D is reacting, it says that E has the ester linkage. Now if E has the ester linkage, definitely then the ethanol chloride has reacted with the OH part of the tyrosine. Now OH part was bonded to the benzene ring, so here should be the ester linkage, and so we should draw COCH3 on this part. Okay, I think I have not drawn it correctly. I can rub and draw it again. Actually, I had cornered the benzene ring, so I could not draw the ester linkage properly, so I'm drawing it again. O here and then double bond O here and then CH3. So this is CH3 COO and then benzene ring. So here is the ester linkage, and then we can draw the remaining structure without any change. So here is the remaining structure where the carboxylic and amine group remains the same. Now in F, it shows that the ethanol chloride doesn't react with the alcohol group, that is phenol part, to form the ester linkage, because then there is no ester linkage in F. That shows that the ethanol chloride CH3COCl has reacted with the amine group of the tyrosine. So that shows that the benzene ring with the OH group should remain the same, and then the amine group gets the linkage that reacts with the ethanol chloride. So let me draw NH, but then I'll draw a amide linkage here showing NHCOCH3. So here is the remaining change, or you say there is no ester linkage, but then there is an amide linkage here forming NHCOCH3. So CH3CO reacts with the amine group, and this is the structure of F. Let me rewrite it properly because it wasn't very clear. So now I think it should be clear. NHCOCH3. Let's go ahead with the C part of this question. It says complete table 9.1 drawing the structure of organic products formed when tyrosine reacts with each named reagent below. Ignore the directing effect of the CH2, CH, NH2, COOH substituent. So this group is not going to affect the directing part of the benzene ring. And so the first reagent here is an excess Br2 is used, excess bromine is used. So if we have a phenol group in our tyrosine, then this phenol is going to direct the bromine group on the second and sixth position, because the fourth position is already occupied by the remaining part of the amino acids. So let me finish that part. So what is main part here is that only the phenol ring is substituted by bromine, and the other parts of the amino acids, that is the remaining part of the amino acids, remains unchanged. Next reagent is excess NaOH. Now as we know that the phenol is acidic, so it's going to react with the basic NaOH and form a salt. So again the NaOH, that is the base, is going to react with the phenol part. You can leave the structure like this with a negative charge on the benzene, on the O part, that is oxygen. But there is another method of presenting the structure here. You can write Na plus also. These are both methods acceptable. You can leave only with O minus, or you can write Na plus and O minus also. Next reagent is an excess of HNO3, nitric acid. Again nitric acid will substitute the nitro group on the benzene. Now we already have alcohol, so the nitro group can be directed to the second or fourth position or on both position. Now let me specify here, if we have dilute nitric acid, it gets directed to the second, fourth and sixth position. But as we know that the fourth position is already occupied by the remaining part of the amino acid, which I am drawing as the same here, unchanged here. So you can draw only one nitro group on the second position, or if it is concentrated HNO3 nitric acid, then all the three positions, that is second, fourth and sixth position, gets substituted by nitro group. Here it is not mentioned whether it's dilute or concentrated, so you can leave the structure with only one nitro group, or you can add another nitro group on the sixth position of the benzene ring also. Both is acceptable, and you can draw any one which you feel is fine for you. Next part of this question is, let's see, D part, where the end of the question paper is here. Last question of this question paper 4.2. The D question says a mixture of tyrosine and lysine can be separated by a thin layer chromatography under certain conditions of RF value. Lysine is 0.14 and the RF value of tyrosine is 0.45. Explain what is meant by the RF value. Now, as I had already mentioned in our earlier videos, that there are few definitions which we should definitely learn. See, this is the third definition which we have come across in this question paper. So what's the definition of RF value? RF value is the ratio of distance traveled by solute, but here our solute is amino acid, so we can specify traveled by amino acid divided by the distance traveled by solvent. So that's the ratio of both this distance, and that gives us the RF value. And next sub question says, suggest an explanation for the difference in the RF value. Now we can see that the RF value of tyrosine is greater and the RF value of lysine is very less. Now if tyrosine is having higher RF value, that shows that the tyrosine was absorbed more on the thin layer chromatography. So one of the reason can be that the tyrosine is more soluble in the solvent. Tyrosine is more soluble in the solvent used. Or you can also say that the lysine was more attracted to the stationary phase of the thin layer chromatography. That's why it traveled less distance. That also can be one of the reason. I have mentioned one reason here, and so this is the end of this question paper 4.2. Last question. I hope all the questions are very clearly explained, and if there is any doubt, you can leave any questions, any queries in the comment box, which will be solved by me whenever I find it.